Now, for the Cenozoic, so the past 65 million years or so, there have been a number of academic studies trying to model it, and with paleoclimate models. And I have used the one from Stapp et al. In 2017. There's also other climate models using oxygen isotopes as well. So for the Cenozoic, we have a relatively good understanding how the system works and what the variations would have been. My interest, however, is going further back in time, and we don't have these detailed models at this kind of short time steps, and we don't have the enough oxygen isotopes data either to do this. So in a way, I had to come up with by using the Cenozoic and the information that we know from that. Can I get some learnings from that and apply that to the Mesozoic and the Paleozoic or the Neoproterozoic going further back in time? And I did so in the following way. So in the light gray, you see all the cyclicity, this sort of bit the noisy background here, um, which are all these short-term cycles. And this is in 1,000-year steps. Now I quantified an average, so that's the dark gray line in 1 million year steps, which is the same time step that I used for my long-term reconstruction in 2022 in the light blue. And I also quantified what are the hottest periods, so the 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 minima, the interglacial periods, and what are the maximum glacial periods, so what are the coldest times within those short time steps. And we also know that since about 30 or so million years ago, the Antarctic and Greenland ice caps have been growing. And you can sort of see that there's some variation in the beginning, but in terms of sea level, it's only a few tens of meters in this short-term signal. Whereas more recently, in the past 5 million years, we've got global mean sea level varying by over 100 meters. So it seems that the fact that you've got long-term ice getting more and more and more, also creating more variation in the shorter term. And obviously, if you go into the extreme, going further back in time, where there's no ice whatsoever, then there's also no sea level variation as a result of ice. So I try to quantify this relation in the following way. In gray, you see the same variation in these 1,000-year steps. Then in red, there are the 1 million year averages through the Cenozoic. And in part, we are limited by the amount of land available. So Antarctica, as you know, is surrounded by an ocean. So ice can't grow further beyond that. No further land ice, at least. So there's a factor in here that limits the amount of potential ice that could grow in the world. So, but if you then look at the extremes, so then I defined the light blue line, which sort of captures what's the ultimate maximum of ice that I could expect that's been growing, that could potentially grow in the world. Now, in the Cenozoic at the moment, on average, it's maybe varying between 0 and 50 million cubic square kilometers. And which the Eocene is ice-free. And still, we know there's a temperature variation happening of about plus minus 1.4 degrees centigrade. That's relatively well constrained with some new studies. Whereas if you go, let's say, the Miocene, where you've got 30 million cubic kilometers of ice, then the temperature variation that was happening at that time is about 2.5 degrees centigrade. So you can see that these are quite significant temperature variations that are coming out of this paleoclimate model as a result of effectively having long-term ice. Now, as said, if we would have had direct evidence from oxygen isotopes and so on, then we could maybe calculate this directly. But we had to do this sort of bypass to get to this reconstruction for the Phanerozoic, where we don't have all this detailed temperature data. So using these temperature variations as a function of long-term ice, we then derive the short-term variations in set temperature, but then also the latitude on which ice can be formed. Then we quantify the amount of volumes of land and shelf ice, and then as a result of that, we can quantify amount of sea level change, so glacio-eustacy. And I just want to point out, I've been focusing on the maximum potential variation, but if needed, I've also got models where I just calculate what's more or less the average as well. But let's stick with the maximum variability for now. So for paleo-temperature variations through time, it's a bit hard to see, but in the hot Jurassic and Cretaceous, there's relatively limited temperature variation. Whereas in the late Neogene and present day, and also in the Permo-Carboniferous, you have a larger amount of variation in temperature, as I was already showing what I derived for the Cenozoic. Now, that results then in what latitude can you have perennial ice formed, so permanent ice sheets at the poles. And minus 10 degrees centigrade is usually what the climate modelers use. That's something, a temperature that you need to really have ice growing and being retained there during the summertime. So, and you can see then the latitudes have been changing over time. So at the moment it's about 60 degrees latitude, north and south, whereas in the Jurassic and Cretaceous, it was at 80 degrees latitude, for example, or maybe at 90 degrees. So basically the times when there was no ice at the poles. From that, you then calculate, okay, how much land do I have within the ice latitude? And with some assumption, you can also get to a thickness of the ice and therefore leading to volumes. So in the Cenozoic, you have a large amount of ice and also varying. So the light blue, remember, is the shading. The light blue shading is the short-term variation in this. So it's more clearly in the Permo-Carboniferous. So long-term, yes, there's a lot of ice here at that time. But short-term, there's also tremendous amount of variation potential here as well. Whereas in the Jurassic and Cretaceous, this variation is far less. So translating that from ice volumes in glacio-eustacy, then present day, you get to about more than 100 meter sea level change as a result of the ice ages coming and going. The same for the Permo-Carboniferous and the Jurassic and Cretaceous, there was a very minimal amount of glacio-eustacy or nothing at all. For example, in the Cenomanian-Turonian here in the mid-Cretaceous. This is just another way of displaying the same graph. So the variation from the long-term average. So basically sea level going up and down by plus minus 60 meters at present day. And I said the Jurassic Cretaceous is relatively minimal. So that came basically using the glaciostatic variation in the short term, plus all the other previously published curves that got me to this graph that you've seen before, and it was also part of the abstract for this talk. Okay, so now, does this work in practice? Do we understand, we may understand sea level change globally, but does it actually behave and dictate sedimentation in basins? That was a big question for me, and that's what I'm testing in many basins across the world through my work. There's also other published curves from Bilal Haq in particular. Yeah, and I did a bit of a qualitative assessment. Are we in agreement? So he based his on sequence stratigraphy, although in many cases not particularly publishing what he has based it on. Whereas my reconstruction comes from isotopes. And you can sort of see in this let's say hundreds of millions of years, we've got a sort of similar pattern. So mine is in dark blue and light blue here. And it sort of follows the same rhythm, sea level rising in the Jurassic and falling in the Cenozoic. And Huck has got the same, although his pace is a little bit less steep in the Jurassic, but we get to sort of similar level in the Cretaceous and the early Paleogene. Now, if I go into the short-term signal, though, we are very, very different. So his short-term variation is actually very similar to mine. We don't entirely agree on the timing of it, but it's sort of similar amplitude of about 100 meters variation. But then in the Jurassic and the Cretaceous, he stays with about 100 meters variation, whereas in my case, I have a few tens of meters maximum. So there's a very big difference between his analysis and mine, which needs further study. Either, let's say, he might be wrong, I might be wrong, or we might both be right, but there is still something happening out there that we don't fully understand yet. Going further back in the Phanerozoic, so briefly you saw an overview until the Jurassic. So now I also compared it with a number of different basins, some literature studies, which are the bold lines here. And you can sort of see that for Jurassic and Cretaceous, that those studies agree with my analysis, at least in amplitude, maybe not entirely in timing. So both Jurassic and Cretaceous, also in the Permo-Carboniferous, I've got relatively high estimates of short-term variation, as do those studies have, whereas the Huck's curves are much significantly lower. And also in the Silurian or the Vision, I suppose we all agree. So both Huck's curves, my curves, and some of the literature agree in this short interval as well. So as I said, I applied this knowledge to some of the basins that we're studying through my oil and gas exploration work. So in one case was the Scotian Basin in Canada. And this is a stratigraphic column for this basin, which was studied in many different analysis, most recently by a company called Dicey Franlab, and there's a lot of material on that, which I've partly incorporated in this presentation, but there's much more in the backup if needed. Anyway, so they've tried to map this or constrain this as much as possible with the most recent geological timescale. And why did they do this? Well, there's some economic interest behind this because there is quite a lot of oil and gas found in this basin on the shelf in a number of different reservoir levels in the lower Cretaceous and upper Jurassic. There's also a source rock which is not entirely well constrained, but is thought to be somewhere in the upper Jurassic. So that's the reason why this basin has been very well studied and therefore is such a good test case for my sea level curve. If you go into the second order signal in my sea level curve, you basically have this rising and falling sequences here, which what I always find the most easy to correlate with stratigraphic diagrams, as you've just seen, is the maximum flooding times, which I've abbreviated as MFTs here. So they occur at 5 different times in theory and during the passive margin stage of this basin. In the earliest Jurassic, this basin was still breaking up, and local tectonics is therefore quite messy. But potentially is another peak there as well, which maximum flooding there as well, which I'll come back to in a moment.